All right. So last time we started with acid-base chemistry, and if you remember from class yesterday, if you're in Dr. Reed's class, y'all started with the same thing, right? So we said there's the theory that we're going to focus on right now is Bronsted theory, and acids donate protons, bases are proton acceptors. So they're going to take bases take protons away from acids. And so when we look at example one, we can see that yellow highlighted proton is removed from the base on the right next to it. So this is bicarbonate. These electrons form a bond to this hydrogen, and that hydrogen or that proton breaks this this bond here breaks, and those electrons go onto the oxygen. All right. So that's just a simple proton transfer reaction. And so then we had y'all do another one where you have methoxide, and those methoxide is negatively charged and it's going to deprotonate the acidic hydrogen on phenol, which is that one attached to the OH. So I didn't draw the arrows, you can draw them yourself if you have an idea of what's going on. But basically these electrons are going to attack that proton, and hydrogen can only have one bond, right? So if you form a bond to this hydrogen, that means you have to break another bond. And because this is the acid, we're going to donate the proton, and so we're going to break this bond. It's going to go into that. Those red electrons are going to go onto the oxygen and get a negative charge, and you form methanol as your conjugate acid, right? So we have our acid turns into our conjugate base, and our base turned into our conjugate acid. Any questions so far?
Can you explain the conjugate acid and conjugate base?
Yeah, so basically we start with an acid on this side, right? And we lose a proton and we end up with a negative charge. Bases have negative charges. So your acid forms your conjugate base. Okay. On the other hand, we start off with a base here. Base has a negative charge. It takes on a proton, so it becomes more acidic, right? Because acids have protons. If this is gaining a proton, it's becoming more acidic, so it's our conjugate acid. Does that make sense? Yeah, okay. So conjugate acid-base pairs. So conjugate base is derived by removing an acid, the proton, and then our conjugate acid is derived from adding a proton. We talked about the quantitative measurement of acid strength. So again, you don't need to know the definition. You just have to know what this means. General, let's see, a general acid dissociation reaction is when the HA produces H plus and A minus. And we know that when we're doing equilibrium expressions, it's products over reactants. So it's going to be H plus over A minus over HA. We use this to determine how strong an acid is or maybe how weak it is. So in organic chemistry, we actually use the negative log of the Ka, which is the pKa. It's just an easier way to express that value of how strong or weak an acid is. Because if a Ka is 1 times 10 to the minus 5, the pKa is just 5. So when you're talking to someone and saying this acid has a pKa of 1 times 10 to the minus 5, it's easier to say this acid has a pKa of 5, right? Yeah.
And then if you make a conjugate base, you get the K divided 14 minus 5.
Yeah. It is more.
Oh.
Mhm.
So basically the pKa is to make the, to reduce the number, kind of like make the variable small. With that, it's kind of like to put the number as small.
It's easier to say it.
Yeah, so it's exactly, it's easier to say the number. So they both mean the same thing. A Ka of 1 times 10 to the minus 5. When you put that into this equation here, you can just get a pKa of 5. It's a way of expressing it differently. So instead of saying, you're saying the exact same thing, it's just two different numbers. Yeah, exactly. Yeah, so it's just easier to talk to people in conversation using pKa than it is Ka, because Ka can have a lot more digits and it's just longer to say. All right. So as acid strength, and we talked about the inverse relationship between acid strength and the strength of their conjugate base. So we know as acid strength increases, so if we have a strong acid, then we know that the conjugate base is going to be really weak or stable. So our examples were HCl, pKa of -7. Remember, low pKa indicates strong acid. It dissociates into H plus and Cl minus. Because this is a strong acid, that means its conjugate base is weak. And then vice versa, we had ammonia, which has a pKa of 38, and you recall that a high pKa indicates a weak acid. So this is a weak acid, very weak acid. So when it dissociates into H plus and NH2 minus as its conjugate base, it makes a super strong conjugate base. Yeah.
So if you had a question just be rank group, that's telling you rank NH3 and NH2 minus, and it says rank them based on the stronger base. The stronger base would be NH2 minus because you have a negative charge, right?
Yeah, that's pretty much it.
And then the weaker, and then I would, if you're ammonia, that would be weakest, right?
But it has no null pairs, first of all.
Yeah, exactly, it's
Yeah.
a plus charge.
It's a plus charge, and it can't even accept a proton at that point because it has all four. Its octet is completely filled with bonds, no lone pairs, so it's not able to grab onto anything without a lone pair.
If it were to have, sorry, if it were to have a positive charge, it would be the weaker base out of all, right?
Yeah. Typically, the things that have a +1 formal charge are gonna not be basic whatsoever because they want to get rid of their protons. They're better acids than they are bases. Yeah, you had a question?
No.
Oh, sorry.
So we only want to memorize the case for the acids to know the base.
You only have to memorize the pKa's of the acids to know the bases. What do you mean?
So if I memorize like the pKa's of NH3, then I can know if its base is strong.
Yeah, so you know that this is based on the pKa, you know this is very weak, right? Because it's super high pKa.
And the base will always be strong.
If it's dissociates into this, but 9 times out of 10, it's not, or 10 times out of 10, it's not going to be over here. Equilibrium most likely favors, or it does favor the acid. So this reaction here is probably not going to happen just because its K or pKa is so reactant favor and not product favor. But yes, that's how you can tell. We're just going over a review of what we did last time before we go into some problems. And then we did some steps to complete acid-base reactions. So identify acid and base, then complete the reaction. Identify conjugate base or acid-base pairs, and then determine which acid is weaker. So remember, we're looking at the acid on the left and the conjugate acid on the right. We're not looking at the bases or conjugate base. And then once we determine which acid is weaker, we can figure out which way equilibrium favors, which way the reaction favors based on where the weaker acid and base are. All right. Any questions so far? We're good. Okay. And we went over the higher method to determine acid strength, or to determine the stability of its conjugate base, which will tell us how strong the acid is, right? Because the more stable the conjugate base, that means the weaker the conjugate base, which means it came from a stronger acid, right? So we did the element effect. Basically, the atom with the negative charge that has a higher electronegativity is going to be more stable because it's able to stabilize the negative charge better. So we had O minus and N minus here, right? So oxygen with a negative and nitrogen with a negative. Well, oxygen we know from the periodic table is more electronegative than nitrogen, so because of that, it's going to be more stable, which means it came from a stronger acid, right? Does that make sense? Yeah? Vice versa, this one is not as electronegative as oxygen, therefore it's not as stable as this one. Because it's not as stable, that means its stronger base came from a weaker acid. Remember the indirect relationship between acids and their conjugate base. So a strong conjugate base indicates a weaker acid. A weaker or more stable conjugate base came from a stronger acid. And the pKa value should prove it. The pKa of methanol is about 16 and the pKa of methylamine is about 38. Yeah, we're all good? Then we said size is also an important factor. So we use oxygen and sulfur here. The larger the atom is, the better it is at delocalizing that charge over, has more surface area to delocalize it. So we know S, according to the periodic table, sulfur is larger than oxygen. Therefore, it's more stable when it has a negative charge. If this is more stable than this, which one's the stronger acid? This one or this one? A or B? B, right? Because this is more stable, which means it came from a stronger acid. Remember, we think of stability, being stable, as being weak because you're not able to do as much. All right, in a reaction. Things that are stable are low in energy, they're not very reactive. Yeah.
So if you're comparing so I compare the bases, right?
Yeah.
I mean, it's the same thing, but if you're comparing the two, and they're like almost identical, but one has just one more resonance structure, would you say that that one is more stable because it points to the other?
Yeah, exactly. So that's what we're going to get into next. But the more resonance structures you can form, that means the negative charges delocalized over even more atoms. So that's going to cause it to be more stable. So we said resonance stabilizes the conjugate base because instead of it being localized on one atom, we can draw resonance structures that show, hey, this negative charge is actually on two atoms. So it would be on these through resonance. So you stabilize that negative charge by delocalizing it over two atoms instead.
And then when you're drawing these resonance structures, is it okay to sometimes have only one arrow moving or sometimes 3 arrows moving?
Like in this case, you have to have 2 arrows moving because if you put this bond here, that it would exceed the octet on carbon, so you would have to move this one up.
Yeah, but sometimes you can just only draw one arrow.
Yeah, sometimes you can only draw 1 arrow, and if you can do that, and if the question's asking draw as many resonance structures as you can, then if you can only draw 1 arrow at a time, that's your best bet.
But it's okay to have 3 arrows moving also.
Yeah. Inductive effect is just delocalization of the negative charge through sigma bonds. So all sigma bonds are just single bonds. We're not dealing with double or triple bonds. Okay. So we have 2 examples here. One with the only difference is the 3 fluorines over here. And I kind of highlighted what I would think the distribution of negative charge would be, because on the first example, we have all the negative charges localized onto that oxygen atom, right? On the second one, because the inductive effect of fluorine's the most electronegative element on the periodic table, it pulls that negative charge throughout the molecule and you end up with something like this. So it delocalizes it over a greater area. So you can think of that as kind of calming the storm down a little bit, stabilizing that negative charge, because it's instead of it being localized in one area, it's spread out, right?
It doesn't mean it's full.
It doesn't, we're not really talking about polarity right now because this molecule is going to be polar, but it's stabilizing the negative charge. We're only talking about stabilizing the effect of that negative charge right now. Yeah.
You have like an easy way to know like when it's delocalized or localized on here.
Yeah, so if it can resonate, it's delocalized.
Typically, if a carbon has sp2, there's going to be resonance.
Yeah, so I like to just say if you can draw resonance structures for a lone pair, it's going to be delocalized. So you might have to brush up on resonance rules and stuff. Resonance structures are just the same structure, but the different arrangement of atoms, right? So that's a very important thing, especially for this chapter 2. Everything builds off of the previous chapter. So in chapter 1, we talked about resonance. Now we're talking about how resonance stabilizes conjugate bases. And last one was the hybridization effect, which basically says the more S character you have, increasing S character for a lone pair for that negative charge, will stabilize the conjugate base, because we said s orbitals are smaller orbitals. Smaller orbitals are closer to the nucleus. The electrons want to be closer to the nucleus because they're positive, negatively charged, and the nucleus is positively charged. So that's a stabilizing effect when they're close together. So the more s character you have means they're closer to the nucleus, which means more stable. So if this is the most stable because it has the most s character, it's sp hybridized, that means it came from the strongest acid, which has a pKa of 25. And this isn't really a strong acid, but relative to the other ones, it's strong, all right? So it's a stronger acid than the other ones. This one has 33% S and 2 P's, so it's 67% P. So it has less S character than this one, which was 50-50. So because it has less S character, the electrons are not, the electrons of this lone pair that got put on there when you remove this hydrogen are not as close to the nucleus as these electrons. So because these electrons are not as close, it's going to be less stable than this one. Because it's less stable, it's going to be less acidic, right? Because it's another way of saying less stable is it's stronger base, a stronger conjugate base, which means it must have came from a weaker acid. Remember, weak acids make stronger conjugate bases. And then all
SP3 is a strong conjugate base?
it's the strongest conjugate base, yes, because it has the least amount of S character, which means those electrons are really far out from the nucleus. They're not stable, which means they're unstable, which means it's a strong base, right? Stable means weak, unstable means strong. Okay,
And SP3 has the S character.
of 25%, because it's, you can think of it as S and 3 P's. So it's 25% S, 75% P, because it has the 3 P orbitals hybridized. But yeah, so because it has the least amount of S, that means it's the most unstable, which means it came from, it's the strongest base, which means it came from the weakest acid, which is shown with a pKa of 50. Okay, that's it. Now we can go on to some problems. No, not yet. Just jot it down. Okay, let's see where we want to start. This is a good one here. So before we move on to the reactions. So for each pair of compounds below, identify the more acidic compound. So let's start with A. We're going to, so they're asking us which of these acids is more strong. And if someone asks you which of these acids is more strong, what do you respond with?
Let's look at the conjugate base.
Let's look at the conjugate base to determine which one's more stable, because acid strength is indirectly proportional to the strength of its conjugate base. So we can't really tell how strong the acids are just by looking at them. We have to look at how stable their conjugate bases are. So what's the conjugate base for the first one, and how do we know? Where's the acidic proton on this one? Yeah, it's on the oxygen, right? Because these are on the carbon, and we know that those are the least acidic protons in the entire universe. So it's usually going to be on your heteroatom, which is just a non-carbon atom, okay? So in this case, it's oxygen. So this is our acid. So what does that mean for that proton? Is it going away? Yeah, so we end up with, so initially we had 2 lone pairs, now we have 3 lone pairs with a negative charge. Does that sit right with y'all? How we got that? Yeah, are we good back there? No? So we're not showing a base, we're not doing a reaction, we're just looking at its conjugate base. But we know, oops, wrong thing. We know that some base would come and deprotonate this and do that. And then your resulting structure would be this. That's our conjugate base, all right? But we're just not dealing with the base, we're just drawing the conjugate base based off of what would happen if you did react this with the base. We're not doing a reaction though. We're just trying to figure out which of these is the stronger acid or the more acidic compound. So what's the second one? Over there in the back. What's the conjugate base of this? Well, what's happening if you treat this with the base? Well, an acid donates a proton. So we're removing a proton if this is an acid. So right now it has, yeah, so it would have 3 lone pairs and then a negative charge. Remember, we're dealing with acids, so acids donate protons. This is the most acidic proton, so it's going to donate that proton off, and in return it gets a negative charge. So now we have to look at the stability of its conjugate bases and compare them. Yeah.
How, like, in order for the to fulfill the objective, like, could we know some of the elements in the periodic table?
Have an expanded offset. Yeah, you're not gonna deal with expanded offsets in this class, all right, because we're strictly dealing with like second period elements and then a lot of third period elements, but because they're all bonded to like things like carbon, they're not gonna expand their octets. There's some reagents that will, but they're further down the line. For the most part, we play with the octet rule, okay? All right, so now how do we determine which conjugate base is more stable? Yeah, we use higher or reverse higher. I just say higher, but nah, Aereo is weird. No, it's not. Higher, okay. So the first thing we look at is what? Element, right? That's what the E stands for. You said that, electron? Well, that's, yeah. So that's one thing. That's one aspect of the atom effect. But for things that are on in the same group of the periodic table, we look at the size. So oxygen and sulfur are on the same group. So we don't look at the electronegativity. We look at the size. Because down a group, size dominates. Down a period, left and right, electronegativity dominates. So which of these is going to be larger? Say louder. Sulfur, yeah. So sulfur is larger. If sulfur is larger, does that mean it can stabilize that negative charge better, or it's not as stable? It can stabilize it, right? It's taking those 2 electrons and spreading them out in a larger area, so that way they don't have to interact as much. So this is more stable. Another way of saying that is that it's the weaker base. If it's the weaker conjugate base out of the 2, what does that mean for the acid that it came from? It's stronger, right? So the thiol, the one with the sulfur hydrogen, this one here highlighted in, let's do yellow, is our answer to the stronger acid or more acidic acid that the question's asking for. Now we look at this one. Yeah, go ahead.
The conjugate, the acid is the conjugate base stable, the acid is strong.
Yeah, because remember, stability in chemistry means weak. So they are indirectly proportional. So the weaker conjugate base came from the stronger acid. If we had a stronger conjugate base, that means it came from the weaker acid. See how there's the indirect relationship. So in this case, we had a weaker conjugate base, meaning it came from the stronger acid. Now, what do we do for? Go ahead.
most likely gonna be for the size.
So the first thing you look at is element effect. If they're in the same group, meaning going down the periodic table, you use size. If they're in the same period, meaning left and right of the periodic table, you use the electronegativity. Yeah, so always keep in mind, it's not always going to be electronegativity, it's not always going to be size. It depends on where those two atoms are located on the periodic table. All right, let's do B. So I'm asking y'all, how acidic are these compounds? What do y'all draw out? Yeah, conjugate base. So this one turns into the same thing that we had earlier. I'm going to stop drawing lone pairs because y'all need to get used to not seeing lone pairs and just negative charges. Okay. So what do we use to determine the stability of the conjugate base? So we use the higher method, right? So the first one we look at is what?
Element.
I know, I want them to also participate. So the first one we look at is element, right? That's the ranking. Is the element different? Can we compare the elements that the negative charge is on? They're the same, right? So we can't use the element effect to see which one's more stable because they both have negative, or they both have a negative charge on the oxygen. So this is no bueno. What about, and then what do we go down to next? Resonance. So we're looking at resonance now. Which of these has resonance structures that you can make? So yeah, the one with the double bonds, because look at right here. Pay attention. We have a hydrogen here. This carbon already has a full octet. We cannot resonate into it because if we did, we would have to break sigma bonds, not pi bonds. So these lone pairs resonated into here, or not that one. If these lone pairs resonated into here, you would exceed the octet on that carbon atom unless you broke another bond. But we're not breaking bonds in this class, sigma bonds, okay? Only pi bonds when it comes to resonance structures. So that's no resonance. Whereas this one here, we can resonate this down, and this carbon in red, if you resonate that carbon, or if you resonate those electrons down, you would exceed the octet on that carbon unless you did what? Put those pi bonds somewhere else. So let's put a pi bond into let's turn that pi bond into a lone pair. So these electrons I'll change the color. These electrons in blue will move onto this carbon instead, and you'll end up with a resonance structure.
Because I'm like, with huge pi systems like this, it's like, I could just move that pi bond over, but at the same time, like, I could put it on the carbon, so like, what would be your tip when drawing it? If you could put it on the carbon, move it to the carbon first, and then make it a pi bond?
Yeah, that'll give you like more resonance structures. You could do that. That would be fair. And now we end up with a negative charge on that carbon. So we could also do it again, right? We can move this lone pair on to form a bond right here. But if we did that, we would have to move this one onto that carbon. Right? This is just back in chapter 1, resonance structures. All we're doing now is drawing resonance structures. We jump back to chapter 1. We're not even doing acid-base chemistry at this point. We're just drawing resonance structures. But the more resonance structures that we can draw indicate what? It's more stable, right? Because you can delocalize that charge over more atoms. See how it was first, the negative charge was on that oxygen atom? Now, when you draw that first resonance structure, that negative charge gets put on a carbon atom. You can draw another resonance structure where it gets put on this carbon atom, and then another one where it gets put on this carbon atom. So you're delocalizing it. If you were to draw a hybrid, you would end up with something like this. And then you would have a partial negative here, partial negative here, partial negative here, and partial negative here. See how we have partial negatives now on 4 atoms rather than just 1 atom where it has a full negative charge? That delocalization allows it to stabilize the negative charge because it's on 4 atoms instead of just 1. Yeah.
And then what if you have an atom that's like at some point it's negative and then at some point it's positive?
How could that happen?
Atoms. Dr. Aguilar said the partial positive slash negative, but in the test I said that they just use negative and something positive.
I've never seen, I need to see an example.
It's typically with carbon, so at some point they're negative and then something positive.
Are you talking about something like,
That's two carbon, right? People
yeah, so something like this, if you started with this and you drew a resonance structure like that, and then you got something like a plus charge here and a minus charge here, or you could go the other way and you would have a negative charge on the other carbon.
yeah, but it actually happens like where there's resonance structure where it's positive one thing and negative.
Yeah, I mean,
That's the same.
yeah, I would just want to see it first before I say anything about it, because honestly, I can't think of an example where I remember that happening. So if you have an example, show it to me after class, all right? Next one, we're on to the next. Boom, body bag.
That might be induction, maybe?
You see those fluorines, right? And those fluorines are electronegative at that. You already know it's going to be inductive for sure. But let's see. So someone comes up to you and gives you 2 papers that each has one of those compounds on it and says, hey, which of these is more acidic? What do you tell them?
For the elements slides.
Okay, that's one thing, but you're gonna ask them, okay, well, I'm gonna draw out the conjugate base first, right? To determine the stability of their conjugate base, and then that'll tell you which one was more acidic. So that's what we do. All right, so we draw out the conjugate base, and what does the conjugate base look like for the first one on the left? Yeah, negative on the oxygen, right? Because that is the acid. It donates its proton, right? Because it's the acid. Therefore, if it donates its proton, it's taking on that extra lone pairs of electrons, becoming negative. Second one is the same thing. So y'all, I hope y'all are getting used to seeing organic structures. Where we don't draw carbons and stuff. We only draw hydrogens when they're on heteroatoms like oxygen or whatever. And because you're going to see a lot more of these than you are going to see where you see carbons and stuff. So you have to get used to being able to see what this is. All right. Now what do we do? Now that we drew out the conjugate bases, what do we do to decide which one is going to be more acidic? Yeah, so whatever your acronym is, maybe you use ARIO or higher. If you want to get an A in the class, you use higher. So the first one we go through is what? Always. When we check for element of that, right? So is that going to help us solve this one?
No.
And why is that? They both have the same atom with the negative charge, right? We can't distinguish between oxygen and oxygen because they both have the same electronegativity. What's the next one we look at? Resonance. All right, so no there. What about, can we distinguish the two via resonance? No, right? Because they both are attached to those benzene kind of rings. Benzene is C6H6. Meaning they both have the same amount of resonance structure, right? All right, if that's true, then resonance doesn't work. Next, we go on to what? Induction, right? So we look for, are there any negative or electronegative atoms on any of those compounds that can inductively withdraw the negative charge, therefore stabilizing the negative charge? Yeah.
It has to be more like negative or like heteroatom with a negative charge.
Typically, no,
Like you can have like,
you can have like anything that's electronegative, so in comparison to another atom, so like. If we had bromine or iodine here, that's still gonna inductively withdraw electrons. Better than a carbon atom right here, because this is a CH3 group.
and I don't know where the are. Okay, bro, okay.
So those are all electronegative atoms.
Sulfur,
Sulfur, sulfur isn't really electronegative. It's not really up there. But those halogens like fluorine, bromine, iodine are very electronegative, so they are going to take in electrons from that ring.
so it's gonna be really obvious, so if we put it on a test, you're gonna be like,
Yeah, you're not gonna see nitrogen because like nitrogen's very electronegative, but it's actually does something different when it's on something like this. It doesn't take in electrons, it actually donates electrons. So, but you're not gonna see that in this class. That's something you're gonna see in OChem 2 once you get there. All right, so
we get there.
now you will get there, but it's just when, right? Hopefully at the end of the semester, you'll be signing up for OChem 2. All right, so the one on the left has fluorines, it has the inductive effect. Therefore, it's going to be more blank than the other one that doesn't have the fluorines.
Stable.
More stable, right? So this one's going to be more stable. The one on the left is going to be, let me do this for the YouTube. The one on the left is going to be more stable than this one because those fluorines inductively withdraw electron density from that oxygen with a negative charge and from the ring, right? Therefore, stabilizing that compound more, right? Go ahead, you have a question.
That because of electronic.
Yeah, it's the electronegativity. So the fluorine is has the largest electronegativity value on the periodic table. So it's gonna pull those electrons super hard, delocalizing them even more than it already does with the resonance.
Isn't your mind if the acid is strong without knowing the pKa value?
Yeah, this is how you figure out which acid is stronger without knowing the pKa values. So like I said, you don't have to memorize the pKa values because you can use this, but you're going to take a lot more time using this on a test than if you just had memorized the pKa values. That's why I tell everyone, memorize the pKa values, because although you might know how to determine acid strength based on this higher or REO method, if you don't know how to do it in a timely manner, if you're slow with this, like if you can do it, but it takes a long time, then you're just going to lose time on the test that you could have been skipping on to the more difficult problems, okay? So memorize those pKa values that I told you. So because we said this one's more stable on the left, what does that mean about the acid that it came from? Stronger. It's more stable. This one's more stable, so that means it's weaker, which means it came from the stronger acid. So the one highlighted is our stronger acid. And let's do this one here. Someone says, hey, which of these is more acidic? We say what? What do we say, guys? Yeah, let's look at the conjugate base. So then we see that there is a negative charge on those two carbon atoms. So what do we do to determine which one of those is more stable? Yes, so we go through our acronym, whatever it may be. So first one is what? Element. Can we distinguish which one's more stable based on the element there? No, because they're both carbon atoms. Next one is what? Yeah, resonance. So can we distinguish which one is more stable based on resonance?
Yeah, personally.
No, you cannot, because these orbitals, the lone pair that it occupies, in this case, is an sp2 hybrid orbital, and this one is an sp hybrid orbital. In order to resonate, you have to be in a p orbital. Okay, so there's no resonating here, because if you did, you would break the octet on something. That's another reason, because if we put this here to make, have you ever heard of a quadruple bond? No, because they don't exist. No, I don't know. I guess theoretically they could, but we don't see them, okay? A quadruple bond would form here, and that would give this carbon in the middle 5 bonds, 2 electrons in each, that's 10 electrons on carbon. That exceeds the octet rule. So either way we resonate, we exceed the octet rule, so it's not a valid resonance structure. So resonance is not good either. Can we look at inductive effect? Are there any electronegative atoms downfield? What you're gonna see in this class mainly is gonna be fluorine, chlorine, bromine, and iodine. Okay, do we see any of those on there? No. Therefore, this doesn't work out. The last one is what? This is probably the most difficult one that people have a hard time understanding because hybridization is probably a difficult concept for most people. So can we use hybridization to determine which one? What was that? Yeah, we have no choice, so yes, we can, but how
I
do
can
we?
look at the hybrid of the carbon, which has the negative charge.
Yeah, because we only care about that negative charge, right? We're not gonna look at the hybridization of anything else on the compound. This is a fairly simple compound, so it has 2 atoms that are the same hybridization, but if it was a larger compound, we wouldn't look at any other thing except the one that has a negative charge. So what's the hybridization of the one on the left? sp2. I did mention it earlier, so it is sp2. And how do we know that? Because there's 3 electron regions around it. Double bonds count as 1 electron region. Then we have this other electron region, and then we have this other electron region of the lone pair. So that's 3. sp2. Okay. No problem. All right, what about the second one? So this is sp2. Yeah, how many electron regions do we have around that atom? 1, 2. Remember, double and triple bonds count as 1 electron region because it's in one area. 2. So 1, 2. sp hybridized.
Can you do the other one?
Yeah, yeah. 1 there because we only count double bonds as 1 electron region. 2 here, and then 3 there. sp2. Okay. Got it? Are you sure? Everyone got that? Hybridization tripped me up back in high school, so don't worry. Got it? We're all good? Yeah, okay. So because we said earlier that the one that has more S character is more stable, what does that mean? For which one of these is going to be more stable than the other? The second one, right? Because on the first one we have 1 S and 2 P's, so that's about 33% S character. On this one, we have 1 S and 1 P, which is split down the middle 50-50, so 50% S character. This one has more S character. It's more, that means these electrons are closer to the nucleus, so they're more stable. Because it's a more stable conjugate base, what does that mean about the acid that it came from? Exactly, so more stable. It's also known as being weaker. Because it's weaker, that means it came from the stronger acid. So here we go. Stronger acid. All right.
I never understood the percentage.
You don't, as long as you know 25%, 50%, and 33%, that's all you're gonna see for hybridization in these classes. Okay? All right. So let's move on to number 6. All right. I don't like these problems. I mean, it's not that I don't like them. I just want to do something different. All right. Write the reaction of the proton transfer that occurs when each of the following reacts with water and draw appropriate equilibrium arrows. So these are the types of problems you're going to see in Dr. Reeves' class, okay? So if I remember correctly, I was about to pull up the email, but I don't want to do that while I'm recording. But Dr. Reeves is gonna ask you three main questions. I think I'm forgetting the two. Or forgetting one of them, but the first one's going to be which way does equilibrium prefer based on this reaction? And it favors the weaker acid. And the second one is going to be, can this base dechlorate this acid? And you have to figure that out based on either pKa values or writing the reaction, figuring out which one forms the weaker acid, and seeing if it favors products. Because if it doesn't favor products, that means that base is not strong enough to deprotonate that acid. And we'll see something like that on here. So that way you actually have an idea of what does look like, what those may look like on your test. So this one here, let's start here on the left. What kind of species is that? The negative charge is on what kind of atom?
Carbon.
Carbon atom, right? So this is number one. So that is going to react with what? What is the problem saying? It's saying water, right? It's saying each of these reacts with water. So let's write an acid-base reaction for this. We know it's equilibrium. It's in equilibrium, but we were going to find out which way equilibrium favors later. All right. So what is the products of this reaction? Now remember, this is our base. This must be our acid. But well, maybe it'll help if we draw arrows so it shows what's happening. Where does the arrow start at? The negative charge, right? Because arrows show the flow of electrons. So we're starting where the base is and that negative charge. That's going to attack what? Hydrogen. And if you draw a bond to that hydrogen, what do you have to do? Break the other bond, right? Because this base is taking off that proton from the acid, right? So that acid gains those electrons, and we end up with this. Okay, so now what do? We are asked which way equilibrium favors. And we know that equilibrium favors the formation of the weaker base or weaker acid. Those two are going to be on the same side all the time. Okay, so the weaker base and the weaker acid. So what are the acids in this problem? Say a lot. Water is one of them. So this is our acid. And we know our acid forms our conjugate base, right? Right? Okay. So this is our conjugate base. And we have our base on the left side. That forms our what? Conjugate acid, is that what I heard? Yeah. So conjugate acid. So to determine which way equilibrium favors, we have to figure out which acid is weaker, but we do that by looking at the stability of what? The bases, right? So we're comparing these two strictly. OH minus. So what is the first thing we look at when we're determining the stability of the conjugate base? Yeah, higher or REO, whatever it is. I say higher. So, and the first one we look at is what? Element. We've done this all day today, so now we're back to doing what we did earlier today. We just had to do a little bit more work at the beginning. So which of these is going to be more stable and why? The one with the O, because you're using the element effect, but what aspect of the element effect? Electronegativity. Electronegativity is only applied when things are on the same period which carbon and oxygen are on the same period, so that's valid. And because oxygen is more electronegative, it can what to that negative charge?
Cool.
Well, they're already on it, so it can. What's the word I've been saying?
Stable.
Stabilize that negative charge because it's more electronegative. So this is more stable based on the element effect, the electronegativity element effect, right? Which means it came from the stronger or weaker acid. If this is more stable, think about it. If this is, yes, more stable, which means it came from the stronger acid. So that means which one's the stronger acid?
Water.
Water. So stronger, abbreviated stronger acid, which means the other acid in this problem must be the what? The weaker acid, right? Because if this is the stronger acid, then that automatically that means that the other acid, in this case, is propane because it's a 3-carbon chain, is the weaker acid. And we know that equilibrium favors the formation of weaker acid. So is this product favored or reactant favored? Product favored, right? So if we were to draw equilibrium arrows, they would look something like this. It's mainly wants to go to the right. See how that big arrow says it's going to the right, and very little of the reaction wants to go to the left, right? Does that make sense? Okay. Yeah, no problem. I'm gonna airdrop this right now
Oh, really?
to everyone in class that's able to use airdrop. Yeah, gotcha. All right, stop recording.